There are objects in space that refuse to follow the expected pattern of stellar death. When certain stars exhaust their fuel and collapse, they don't simply fade into darkness. Instead, they transform into something else entirely, something that continues to exist in a state between life and extinction. These are the stellar remnants we sometimes call zombie stars, and they represent some of the most extreme physical conditions the universe can produce without creating a black hole. The term itself carries a certain dramatic weight, but the reality is far more measured and methodical. A zombie star is not truly undead in any supernatural sense. Rather, it describes stellar objects that persist in active states long after the conventional burning of nuclear fuel has ceased. Some are neutron stars, crushed to densities that defy everyday comprehension. Others are white dwarfs that pull material from nearby companion stars, reigniting surface reactions that briefly revive their luminosity. All of them share this quality of extended existence, this refusal to quietly disappear. When you look up at the night sky, most of the points of light you see are active stars, converting hydrogen into helium in their cores, generating energy through fusion that has continued for millions or billions of years. But scattered among them, invisible to the naked eye, are these remnants. They're not producing energy the way living stars do. They're either cooling slowly over cosmic timescales or drawing power from rotation, magnetic fields, or the gravitational harvest of companion objects. They exist in a different phase of stellar existence, one that can last for billions of years or more. The discovery of these objects changed how we understand stellar evolution. Before astronomers detected the first pulsar in 1967, the final chapters of a star's life were largely theoretical. Scientists understood that massive stars would end in supernova explosions, but what remained afterward was speculation. When Jocelyn Bell Burnell noticed regular radio pulses from a point in space, repeating with such precision that they seemed artificial, she had found evidence of a neutron star, an object so dense that a city-sized sphere could contain more mass than our sun. The existence of such an object seemed almost impossible, yet there it was, sending out its lighthouse beam of radiation with metronomic regularity. These zombie stars don't emit light the way normal stars do. There's no ongoing fusion reaction in their cores, generating a steady outward pressure of radiation. Instead, neutron stars emit energy from their rotation and their magnetic fields. Some spin hundreds of times per second, having conserved the angular momentum of their much larger progenitor stars. Others rotate more slowly, once every few seconds, but generate magnetic fields so powerful they distort the very atoms around them. White dwarf zombies shine from residual heat, slowly, cooling over trillions of years, or from material they've stolen from companions, heated to such temperatures by the force of gravitational compression that it ignites in brief thermonuclear flashes. The universe has been creating these objects for billions of years. Every sufficiently massive star that dies in a supernova has the potential to leave behind a neutron star. Every sun-like star that exhausts its fuel will eventually become a white dwarf. There are perhaps 1 billion neutron stars in our galaxy alone, most of them undetected because they're no longer actively emitting radiation we can observe. White dwarfs are even more common, representing the ultimate fate of 97% of all stars. These objects accumulate slowly across cosmic time, a growing population of stellar remnants that will eventually outnumber active stars. But for now, during this era of the universe's history, when star formation still continues, zombie stars are a relatively rare sight. Most are too dim and too far away to observe without specialized instruments. The ones we can study are the unusual cases, the ones that happen to be oriented so their radiation beams sweep past Earth, or the ones in binary systems where we can observe the effects of their gravitational influence on companion stars. These observable cases have taught us most of what we know about these objects, revealing physics at the limits of what matter can withstand before collapsing entirely into black holes. What makes these objects so remarkable is not just their extreme densities or rapid rotation. It's the way they represent a stable end state for stellar matter. A neutron star will persist essentially unchanged for timescales that dwarf the current age of the universe. It will gradually cool and its rotation will slowly decrease, but the fundamental object remains. A white dwarf will likewise cool over trillions of years, eventually becoming a black dwarf that emits no light at all, but even then, it continues to exist, a crystal lattice of carbon and oxygen floating silently through space. In this way, zombie stars are more permanent than living stars. Active stars are constantly changing, burning through their fuel, evolving from one stage to another. But zombie stars have reached an equilibrium. They no longer evolve in the same dramatic way. They simply persist, monuments to the stars they once were, carrying within them the signature of those earlier lives. To understand zombie stars, you first need to understand what it means for a star to die. Death for a star doesn't happen suddenly. It's not like an explosion that ends everything in an instant, though supernovae certainly appear that way from a distance. Rather, stellar death is the culmination of a long process of resource depletion, a gradual running down of the nuclear reactions that have sustained the star throughout its main sequence life. Stars generate energy through nuclear fusion in their cores. Hydrogen. Atoms, under immense pressure and temperature, fuse together to form helium, releasing energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. As long as fusion continues, the star remains stable. The core produces energy, that energy pushes outward, and gravity pulls inward, and these forces hold each other in check for millions or billions of years. But hydrogen is finite. Eventually, the core exhausts its supply of hydrogen fuel. When this happens, the balance shifts. Without the outward pressure from fusion, gravity begins to win. The core contracts, and as it contracts, it heats up. If the star is massive enough, this contraction raises the core temperature high enough to ignite helium fusion. Helium nuclei fuse together to form carbon and oxygen, and the star enters a new phase of its life. This process can continue through several stages, with progressively heavier elements being formed in the core, but each stage is shorter than the last because heavier elements release less energy when they fuse. For stars with about the mass of our Sun or less, helium fusion is the final stage. The core continues fusing helium until it too is exhausted. At that point, the core lacks the mass to compress enough to ignite carbon fusion. Instead, the star begins to shed its outer layers, gently puffing them off into space in a process that creates what we call a planetary nebula. The core that remains is a white dwarf, no longer capable of fusion but still incredibly hot from the compression it has undergone. For more massive stars, the process continues further. Carbon fusion produces neon and magnesium. Neon fusion produces oxygen and magnesium. Oxygen fusion produces silicon and sulfur. And finally, silicon fusion produces iron. This is where the process stops. Iron is the most stable nucleus in the universe. Fusing iron doesn't release energy, it actually requires energy input. Once a massive star's core has been converted to iron, fusion can no longer provide the pressure needed to support the star against gravity. What happens next occurs on a timescale measured in seconds. The iron core collapses catastrophically. Atoms are crushed together with such force that electrons are pushed into protons, forming neutrons and releasing a flood of neutrinos. In less than a second, a core with a mass comparable to our Sun's and a diameter of several thousand kilometers collapses to a sphere only about 20 kilometers across. The density becomes so extreme that the neutrons themselves provide a degeneracy pressure that finally halts the collapse. This is a neutron star, one type of zombie star. But the collapse doesn't happen in isolation. The outer layers of the star, which have been falling inward, suddenly encounter this incredibly dense core. They bounce off it in what's called a core rebound. The energy from this rebound, combined with the intense neutrino flux from the core, blows the outer layers of the star apart in a supernova explosion. Material that has been processed through nuclear fusion inside the star is scattered into space, enriching the interstellar medium with heavy elements. And in the center of this explosion, often obscured by the expanding debris, sits the newly formed neutron star. Not all stellar deaths produce neutron stars. Stars below about 8 times the Sun's mass don't have enough mass to compress their cores to neutron star densities. They end their lives as white dwarfs, having gently shed their outer layers without a supernova explosion. Stars above about 20 to 25 times the Sun's mass have cores so massive that even neutron degeneracy pressure can't halt their collapse. These cores continue collapsing beyond the neutron star phase, forming black holes. So neutron stars occupy a specific range in stellar death. They're the remnants of stars that were massive enough to end in supernovae, but not so massive that their cores collapsed all the way to black holes. This puts them in a sweet spot of stellar evolution, common enough to be found throughout the galaxy, but specific enough in their formation requirements that each one represents a particular chapter in stellar history. White dwarfs are far more common because they represent the fate of the vast majority of stars. Our Sun will eventually become a white dwarf. In about 5 billion years, it will exhaust its hydrogen fuel, expand into a red giant, fuse helium in its core for perhaps a few 100 million years, and then shed its outer layers, leaving behind a white dwarf core. This core will be roughly the size of Earth, but will contain about 60% of the Sun's current mass. It will be composed primarily of carbon and oxygen, the products of helium fusion, arranged in a crystalline structure. And it will be hot, with a surface temperature initially around 100,000 degrees, though it will cool gradually over billions of years. These white dwarfs don't produce new energy. They shine from residual heat, the leftover thermal energy from their time as active stars. They're supported not by fusion or by any kind of ongoing energy production, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain density. As long as the white dwarf's mass stays below about 1.4 times the Sun's mass, this pressure is enough to support it indefinitely. But some white dwarfs don't remain in isolation. Many stars exist in binary systems, orbiting around a common center of mass with a companion star. If one member of a binary system becomes a white dwarf, while its companion is still an active star, the white dwarf can pull material off the companion through gravitational attraction. This material forms an accretion disk around the white dwarf and eventually falls onto its surface. When enough material accumulates, the pressure and temperature at the base of this accreted layer become high enough to trigger thermonuclear fusion. The surface of the white dwarf explodes in what astronomers call a nova, briefly increasing the system's brightness by factors of thousands or more. These are the white dwarf zombies. They've ended their initial lives, shed their outer layers, and become white dwarfs. But through the theft of material from a companion, they experience a kind of revival, brief bursts of fusion that echo their former glory. Some white dwarfs do this repeatedly, cycling through periods of accretion followed by nova explosions. In this way, they extend their active existence far beyond what an isolated white dwarf would experience. Both neutron stars and white dwarfs represent stable endpoints of stellar evolution. They've reached configurations that can persist essentially unchanged for timescales that extend into the trillions of years. They're no longer evolving in the dramatic way that active stars evolve. They're simply existing, slowly cooling, gradually losing what energy they have left, but fundamentally stable. These are the zombie stars, the remnants that refuse to completely disappear even after stellar death has occurred. The birth of a neutron star happens in violence. When a massive star's core runs out of nuclear fuel, it begins to collapse under its own gravity. This collapse is not gradual. It doesn't take place over millions of years or even thousands of years. The entire process from the moment fusion stops to the formation of a neutron star occurs in less than a second. The core, which moments before was the size of a small planet, compresses to a sphere only about 20 kilometers in diameter. The density increases by a factor of billions, and in the process, most of the protons and electrons in the core are crushed together into neutrons, releasing a tsunami of neutrinos that carries away most of the energy from the collapse. To visualize what's happening during this collapse, imagine taking all the matter in a city-sized sphere and compressing it into something the size of Manhattan. Then compress it more. Keep compressing until individual atoms cease to exist, until electrons are forced into atomic nuclei, combining with protons to form neutrons. The entire concept of atomic structure breaks down. There are no longer atoms with electrons orbiting nuclei. Instead, there is just a sea of neutrons, packed together as tightly as the physics of the universe allows without forming a black hole. This compression is powered by gravity. The star's core has so much mass that gravity overwhelms all other forces. Electron degeneracy pressure, which supports white dwarfs, is insufficient. The gravitational force is so strong that it pushes past this quantum mechanical barrier. Electrons can't maintain their separation from protons. They merge, and the resulting neutrons pack together until neutron degeneracy pressure finally provides enough resistance to halt the collapse. The energy released in this process is staggering. When the core rebounds after reaching neutron star densities, it releases more energy in a few seconds than our Sun will produce over its entire 10 billion year lifespan. Most of this energy is carried away by neutrinos, ghostly particles that barely interact with matter. But even the small fraction that remains is enough to blow the star's outer layers apart in a supernova explosion that briefly outshines entire galaxies. The neutrino burst itself is remarkable. During the collapse, about 10% of the Sun's mass equivalent in energy is released in the form of neutrinos. These particles stream outward from the collapsing core at nearly the speed of light. They pass through the star's outer layers with minimal interaction, escaping into space seconds before the visible light from the supernova follows. On Earth, we've detected neutrinos from only one nearby supernova, SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 160,000 light-years away. Detectors around the world picked up a handful of neutrino interactions, arriving hours before the visible light from the explosion reached Earth. The neutron star that forms from this collapse inherits several properties from its progenitor. Most importantly, it conserves angular momentum. The original star was rotating, probably taking weeks or months to complete one rotation. When the core collapses, its rotation rate increases dramatically. This is the same effect you see when an ice skater pulls in their arms during a spin. The skater speeds up because angular momentum is conserved. When a stellar core with a diameter of thousands of kilometers collapses to 20 kilometers, the rotation rate increases by a factor of millions. The result is a neutron star that can rotate dozens or even hundreds of times per second. The fastest known pulsar, PSR J117482446 AD, spins 7,916 times per second. At this rate, the surface of the neutron star at its equator is moving at about a quarter of the speed of light. If it was spinning any faster, the centrifugal force would overcome gravity and tear the star apart. This puts an upper limit on how fast neutron stars can rotate, regardless of how quickly their progenitor cores were spinning at the moment of collapse. The neutron star also inherits the magnetic field of its progenitor. Stellar magnetic fields are anchored in the star's matter, so when that matter compresses, the magnetic field lines are pulled together as well. The strength of a magnetic field is proportional to how closely packed the field lines are, so compression intensifies the field. A typical massive star might have a magnetic field similar to the Sun's, measuring around 1 to 10 Gauss. When the core collapses, this field is compressed by a factor of about 100 million, increasing its strength to around 1 trillion Gauss, or more. These magnetic fields are thousands of billions of times stronger than Earth's magnetic field. They're strong enough to affect the behavior of atoms, altering the energy levels of electrons and distorting atomic spectra. In the most extreme cases, neutron stars called magnetars have magnetic fields of around 1 quadrillion Gauss. At these strengths, the magnetic field affects space itself, creating what's called magnetic condensation, where the field is so intense that it can convert the vacuum into matter-antimatter pairs. The formation of white dwarfs follows a gentler path. When a sun-like star exhausts its hydrogen fuel, it expands into a red giant, a phase that lasts several hundred million to a billion years. During this time, the star's core contracts and heats up while its outer layers expand. Eventually, the core becomes hot enough to ignite helium fusion, converting helium into carbon and oxygen. This helium burning phase is shorter than the main sequence hydrogen burning phase, lasting perhaps 100 million years for a sun-like star. When helium is exhausted, stars with masses below about 8 solar masses lack the gravitational force to compress their cores enough to ignite carbon fusion. Instead, the core begins to cool, supported by electron degeneracy pressure. The outer layers continue to expand and thin, and stellar winds gradually carry this material away into space. The result is a planetary nebula, a beautiful shell of glowing gas surrounding the exposed core. This planetary nebula expands into space over tens of thousands of years and eventually dissipates, leaving behind only the core, now a white dwarf. This white dwarf is initially very hot, with surface temperatures of 100,000 degrees or more. It shines with ultraviolet light, hot and blue. But there's no ongoing fusion producing this heat. The white dwarf is simply cooling, radiating away the thermal energy it accumulated during its time as an active star. This cooling process is slow. A white dwarf will take billions of years to cool to the point where it no longer emits visible light. Even after 10 billion years, most white dwarfs are still warm enough to glow faintly. The composition of a white dwarf depends on the mass of its progenitor star. Stars like the Sun, which fused helium into carbon and oxygen, become carbon-oxygen white dwarfs. More massive stars, which progressed further up the fusion chain, might leave behind oxygen-neon white dwarfs, or even iron-rich white dwarfs in some theoretical scenarios. The mass of the white dwarf is typically between about 1/2 and 1 solar mass, compressed into a volume roughly the size of Earth. Both neutron stars and white dwarfs form through processes that eliminate the possibility of further fusion. Neutron stars don't contain normal atomic nuclei, so there's nothing left to fuse. White dwarfs are composed of nuclei like carbon and oxygen, which could theoretically fuse into heavier elements, but the temperatures and pressures inside a white dwarf aren't high enough to ignite these reactions under normal circumstances. The fusion that powered these objects during their lives as stars has permanently ceased. They exist now in a post-fusion state supported by quantum mechanical degeneracy pressure, either from electrons in the case of white dwarfs or from neutrons in the case of neutron stars. These formation processes determine the properties that make zombie stars so extreme. The violence of core collapse creates neutron stars with rapid rotation and intense magnetic fields. The gentler process of white dwarf formation creates objects that retain more connection to their stellar origins, composed of recognizable atomic nuclei rather than degenerate neutron matter. But both types represent the same fundamental transition from active fusion-powered stars to inert remnants supported by quantum pressure. They've crossed the boundary from life to death, and what remains is something entirely different from what came before. A neutron star represents matter in one of its most extreme possible states. To understand just how extreme, consider density. The average density inside a neutron star is about 200 trillion times the density of water. If you could take a single teaspoon of neutron star material and bring it to Earth, that teaspoon would weigh approximately 6 billion tons. This is comparable to taking all the cars in the world and compressing them into a sugar cube. This density exists because neutron stars compress matter to nuclear densities. In ordinary matter, atoms are mostly empty space. The nucleus occupies only a tiny fraction of an atom's volume, with electrons orbiting in clouds that extend thousands of times farther from the center than the nucleus itself. But inside a neutron star, this empty space is eliminated. Atoms no longer exist as separate entities. The material is compressed until the nuclei are touching, packed together like marbles in a jar. The density becomes comparable to the density inside atomic nuclei themselves. At these densities, conventional atomic structure ceases to exist. Electrons are forced into the nuclei, where they combine with protons to form neutrons through a process called electron capture. Each merger releases a neutrino, which escapes from the collapsing core carrying away energy. The result is a star composed almost entirely of neutrons, hence the name. These neutrons are packed together so tightly that the entire star behaves like a single, giant atomic nucleus, about 20 kilometers across. The size of neutron stars is remarkably consistent despite variations in mass. Most neutron stars have a radius between 10 and 15 kilometers, roughly the size of a small city. Manhattan would fit comfortably on the surface of a neutron star. This small size, combined with masses between about 1.2 and 2.1 times the Sun's mass, creates the extreme densities. All that mass is concentrated into a sphere that, by stellar standards, is incredibly tiny. The surface of a neutron star is itself an exotic environment. The outer layer is thought to be a solid crust composed of iron nuclei and electrons. These iron nuclei are packed far more densely than iron exists on Earth, but they still maintain a crystalline structure. Below this iron crust, the density increases and the composition changes. The nuclei become increasingly neutron-rich as the pressure forces more and more protons to capture electrons and convert to neutrons. Deeper still, the nuclei begin to deform under the extreme pressure. Instead of remaining spherical, they elongate into rod-like shapes called nuclear spaghetti, or flatten into sheet-like structures called nuclear lasagna. These colorfully named phases represent predictions from theoretical physics about how nuclear matter behaves under extreme pressure. No Earth-based experiment can recreate these conditions, so neutron stars serve as natural laboratories where these exotic states of matter can exist. In the star's core, where densities are highest, the very concept of individual nuclei breaks down. The matter may exist as a uniform sea of neutrons, possibly mixed with protons, electrons, and even more exotic particles. Some theories predict that at the very center of the most massive neutron stars, the neutrons themselves might break down into their constituent quarks, creating a quark-gluon plasma. This is the same state of matter thought to have existed microseconds after the Big Bang, before quarks combined to form protons and neutrons. The gravity at a neutron star's surface is intense beyond everyday experience. The surface gravity is approximately 200 billion times stronger than Earth's. If you could stand on a neutron star's surface, you would weigh about 200 billion times what you weigh on Earth. A person weighing 70 kilograms on Earth would weigh about 14 trillion kilograms on a neutron star. This is roughly equivalent to the weight of all of humanity combined. This intense gravity has observable effects. Light emitted from the surface of a neutron star is gravitationally redshifted, its wavelength stretched by about 30% as it climbs out of the star's gravitational well. Time itself runs slower at the surface compared to distant space, an effect predicted by general relativity. The escape velocity from a neutron star's surface is around half the speed of light, meaning any object trying to leave the surface would need to be traveling at 150,000 kilometers per second. The gravitational field is also strong enough to create observable lensing effects. Light passing near a neutron star is bent by its gravity. This means an observer looking at a neutron star can actually see more than half of its surface at once, because light from the far side is bent around the star and reaches the observer. This effect is called gravitational lensing, and it's been observed in X-ray emissions from the surfaces of neutron stars. Neutron stars rotate, and their rotation rates vary widely. Some neutron stars rotate once every few seconds, typical of young pulsars like the one in the Crab Nebula, which completes 30 rotations per second. Others rotate hundreds of times per second. These millisecond pulsars are thought to have been spun up by accreting matter from companion stars, a process that adds angular momentum and increases rotation rate. The fastest confirmed pulsar spins 716 times per second, though theoretical limits suggest neutron stars cannot spin much faster than about 1,000 times per second before centrifugal forces tear them apart. As neutron stars rotate, they lose energy and gradually slow down. This spin down is measurable and occurs because the rotating magnetic field radiates energy away. Young pulsars slow down relatively quickly, losing a few microseconds of period every year. Older pulsars slow down more gradually. By measuring how quickly a pulsar is slowing down, astronomers can estimate its age and calculate properties like its magnetic field strength. Temperature is another important property. Newly formed neutron stars are incredibly hot, with internal temperatures reaching billions of degrees. This heat is left over from the collapse and from the initial compression of matter to nuclear densities. But neutron stars cool rapidly at first, radiating energy away as neutrinos and photons. Within a few tens of thousands of years, surface temperatures drop to around 1 million degrees. After that, cooling continues, but more slowly. The oldest neutron stars in the galaxy have likely cooled to surface temperatures of only a few 100,000 degrees, still far hotter than any normal star's surface. The interior of a neutron star might be even more exotic than the surface. Theories predict that the deep interior could contain superfluid neutrons, a state where neutrons flow with zero viscosity. Protons in the interior might form a superconductor, a state where electric current flows without resistance. These quantum states exist because of the extreme conditions, and they affect how the neutron star behaves. Sudden changes in the interior, superfluid, for instance, are thought to cause glitches, events where a neutron star suddenly spins faster for a brief time before resuming its gradual slowdown. All of these properties make neutron stars fundamentally different from any other object in the universe. They're not stars in the conventional sense, because they don't produce energy through fusion. They're not planets, despite being similar in size, because they're held together by their own gravity rather than by chemical bonds. They're something unique, a state of matter that can only exist in the aftermath of stellar collapse, sustained by quantum mechanical degeneracy, pressure operating at nuclear densities. They're remnants, but active ones, spinning and radiating and interacting with their environments in ways that make them among the most fascinating objects in modern astrophysics. Most neutron stars reveal their presence through the lighthouse effect. They emit beams of radiation from their magnetic poles, and as the star rotates, these beams sweep across space. When one of these beams happens to point toward Earth, we detect a pulse of radio waves, or X-rays, or sometimes even visible light. This creates the appearance of a pulsating source, which is why these objects are called pulsars. The mechanism behind this emission is complex. A neutron star's magnetic field is not aligned with its rotation axis. Imagine the star like Earth, which rotates around an axis that runs through the north and south poles, but whose magnetic poles are offset from the geographic poles. For neutron stars, this offset is typically much larger, with the magnetic axis tilted at significant angles from the rotation axis. As the star spins, the magnetic poles rotate around the rotation axis, and it's from these magnetic poles that the radiation beams originate. The radiation itself is generated by the interaction between the star's magnetic field and charged particles in the region surrounding the neutron star. The rapid rotation combined with the intense magnetic field creates powerful electric fields that accelerate particles to nearly the speed of light. These particles spiral along magnetic field lines and emit radiation as they accelerate, a process called synchrotron emission. This radiation is beamed outward from the magnetic poles, creating the lighthouse effect. The pulses we detect are remarkably regular. Some pulsars maintain their periods to within 1 part in 10 million or better. The most stable millisecond pulsars rival atomic clocks in their precision, changing their rotation period by only nanoseconds per year. This regularity makes pulsars useful as cosmic timekeepers. Astronomers use pulsar timing to test fundamental physics, including Einstein's theory of general relativity. By precisely measuring when pulsar pulses arrive at Earth, researchers can detect tiny variations caused by gravitational effects, the presence of planets orbiting the pulsar, or gravitational waves passing through space. The discovery of pulsars in 1967 was one of the most important astronomical finds of the 20th century. Jocelyn Bell Burnell, then a graduate student at Cambridge University, was using a radio telescope to study quasars, distant galaxies with bright radio emissions. She noticed an unusual signal, a regular pulse repeating every 1.3 seconds. The signal was so regular it seemed artificial, and the research team even considered the possibility that it might be a transmission from an extraterrestrial civilization. They nicknamed it LGM-1 for Little Green Men. But the Wowcha signal persisted with absolute regularity, and soon Bell Burnell detected another pulsar from a different part of the sky. It became clear that these were natural astronomical objects, not alien transmissions. The precise period and the fact that they were coming from multiple locations suggested they must be rotating objects rather than pulsating ones. The most plausible explanation was that they were rapidly rotating neutron stars, objects whose existence had been theorized but never observed. The first confirmed pulsar, now designated PSR B1919+21, has been studied extensively since its discovery. Its period is 1.337 seconds, and it's located about 2,000 light-years from Earth in the constellation Vulpecula. This pulsar has become iconic in popular culture as well as astronomy. An image of its radio pulses appears on the cover of Joy Division's album Unknown Pleasures, making it one of the most recognized pieces of astronomical data in mainstream culture. Not all pulsars emit at radio wavelengths. The Crab pulsar, located in the Crab Nebula and formed in a supernova observed by Chinese astronomers in the year 1054, emits across the entire electromagnetic spectrum. It pulses in radio waves, visible light, X-rays, and gamma rays. It rotates 30 times per second, and telescopes can detect both its main pulse and a weaker interpulse coming from its other magnetic pole. The Crab pulsar is one of only a handful of pulsars bright enough to be observed optically, and even then it requires large telescopes to see the rapid flashing. The energy powering pulsar emission comes from the star's rotation. As a pulsar emits radiation, it loses rotational energy, causing it to spin down gradually. For young pulsars like the Crab pulsar, this spin down is relatively rapid, with the period increasing by about 38 nanoseconds per day. Over millions of years, the pulsar will slow down until it no longer has enough rotational energy to power the emission mechanism, at which point it becomes invisible at radio wavelengths. These dead pulsars still exist as neutron stars, but we can no longer detect them. Some pulsars are in binary systems orbiting around a common center of mass with a companion star. These binary pulsars have provided crucial tests of general relativity. The most famous example is PSR B1913+16, discovered in 1974 by Joseph Taylor and Russell Hulse. This system contains two neutron stars orbiting each other with a period of about 8 hours. According to general relativity, such a system should emit gravitational waves, ripples in space-time that carry energy away. This energy loss should cause the orbit to decay, with the two stars spiraling gradually closer together. Taylor and Hulse monitored PSR B1913+16 for years, precisely measuring the arrival times of its pulses and tracking changes in the orbital period. They found that the orbit was indeed decaying, at exactly the rate predicted by general relativity for gravitational wave emission. This was the first indirect evidence for gravitational waves and earned Taylor and Hulse the Nobel Prize in Physics in 1993. It wouldn't be until 2015 that gravitational waves were directly detected by the LIGO experiment, confirming what the binary pulsar had already strongly suggested. Millisecond pulsars represent an interesting subset of the pulsar population. These pulsars spin extremely rapidly, completing hundreds of rotations per second. The fastest confirmed millisecond pulsar rotates 716 times per second, meaning it completes a full rotation in just 1.4 milliseconds. At this rotation rate, a point on the equator of the neutron star is moving at about 1/4 of the speed of light. The existence of millisecond pulsars initially puzzled astronomers. Neutron stars are born spinning rapidly, but they spin down over time as they emit radiation. A pulsar that's been around for millions or billions of years should be rotating slowly, not rapidly. The solution to this puzzle came from observing millisecond pulsars in binary systems. Many millisecond pulsars have white dwarf companions, and these white dwarfs show evidence of having lost mass. The current understanding is that millisecond pulsars are recycled. They're old neutron stars that accreted matter from companion stars, and this accretion process spun them back up to high rotation rates. This recycling process can extend a neutron star's active life significantly. A normal pulsar might spin down and become radio quiet after 10 million years or so, but if it's in a binary system and can accrete matter from a companion, it can be spun back up and become active again as a millisecond pulsar. These recycled pulsars can remain active for billions of years, much longer than isolated pulsars. Some pulsars exhibit glitches, sudden increases in rotation rate, followed by a gradual return to their previous spin-down rate. These glitches occur because the interior of a neutron star is thought to contain superfluid neutrons, which can rotate independently of the solid crust. When the crust slows down due to electromagnetic braking, the superfluid interior continues spinning at a faster rate. Eventually, the difference in rotation rates causes the superfluid to couple with the crust, transferring angular momentum and causing the crust to suddenly spin faster. This is a glitch. The Crab pulsar has been observed to glitch multiple times, and studying these events provides insights into the exotic interior structure of neutron stars. Pulsars also occasionally go dark. PSR B1931 Plow 204 has an unusual behavior where it pulses for about a week and then stops pulsing for about a month, repeating this cycle. Another pulsar, PSR J1941 Jo500, stopped pulsing for 580 days before restarting. These intermittent pulsars challenge our understanding of the emission mechanism. Why would a pulsar turn off and then turn back on? The answer likely involves changes in the magnetosphere, the region of space dominated by the neutron star's magnetic field, but the precise mechanism remains under investigation. The lighthouse analogy for pulsars is apt but incomplete. A lighthouse has a single beam that rotates, but many pulsars actually show evidence of two beams, one from each magnetic pole. When both beams are aligned such that they sweep across Earth, observers can see both a main pulse and an interpulse half a rotation period later. The pulsar PSR J16641 plus 80449 shows this double pulse structure clearly. Not all pulsars show both pulses, however, and this depends on the geometry of the magnetic field and the viewing angle from Earth. Pulsar emission isn't perfectly stable in the short term. Individual pulses can vary dramatically in strength. Sometimes a pulse is bright, sometimes it's weak, and sometimes it's nearly absent. But when thousands of pulses are averaged together, the average pulse profile becomes very stable and characteristic of each individual pulsar. This stable average profile is the signature of the pulsar, and it reflects the geometry of the emission region around the star's magnetic poles. The study of pulsars continues to reveal new physics. Observations of pulsars at extremely high energies in the gamma-ray part of the spectrum have pushed theoretical models to their limits. The Crab pulsar, for instance, emits gamma rays with energies exceeding 100 billion electron volts, far higher than theoretical models initially predicted was possible. Understanding how pulsars accelerate particles to such energies remains an active area of research. Pulsars represent neutron stars at their most observable. Without the lighthouse effect, most neutron stars would remain invisible to us, detectable only through their gravitational influence on nearby objects. But because pulsars beam radiation in our direction, we can study them in detail, learning about neutron star masses, radii, magnetic fields, and interiors. Every pulsar observation provides another piece of information about these extreme objects, helping to refine our understanding of matter under conditions that can never be recreated on Earth. In the autumn of 1967, Jocelyn Bell Burnell was reviewing data from a radio telescope at the Mullard Radio Astronomy Observatory near Cambridge, England. She was working on her doctoral research under the supervision of Anthony Hewish, and her project involved using a newly constructed radio telescope array to study quasars through a phenomenon called interplanetary scintillation. The telescope produced chart recordings, long strips of paper with traces showing radio signals from the sky, and Bell Burnell's task involved analyzing these recordings for interesting signals. On August 6th, she noticed something unusual in the data. There was a bit of scruff, as she called it, about 200 feet of chart recording showing a signal that didn't fit the pattern of typical radio interference. Most interference came from terrestrial sources like automobiles or electrical equipment, and it looked random and irregular on the charts. This signal had structure. It looked different enough that Bell Burnell marked it for follow-up observation. Getting a follow-up observation wasn't simple. The signal had appeared from a specific region of sky at a specific time, and the telescope was fixed in position, meaning it could only observe that part of the sky when Earth's rotation brought it into view. Bell Burnell had to wait for the right time and weather conditions. When she finally managed to catch the source again in November, she discovered something extraordinary. The signal consisted of extremely regular pulses, repeating every 1.337 seconds. The regularity was striking. Natural. Astronomical sources typically don't produce such precisely timed signals. Stars twinkle, but not with metronomic regularity. Pulsating variable stars have periods measured in hours or days, not seconds. The signal's period was constant to within a small fraction of a second, far more regular than seemed possible for any natural process the research team was familiar with. This raised an uncomfortable question. Could this be an artificial signal? The possibility that the signal might be from an extraterrestrial civilization was taken seriously enough that the team nicknamed it LGM-1 for Little Green Men. Bell Burnell later recalled feeling frustrated by this possibility. As she put it, here she was trying to complete a PhD in astronomy, and the universe had inconveniently decided to present her with what might be evidence of alien intelligence. If it turned out to be an alien signal, her PhD research would be derailed by the ensuing media circus and scientific investigation. But the team continued to search for more prosaic explanations. One possibility they considered was that the signal might be terrestrial interference that just happened to be very regular. However, the signal maintained its timing despite day-to-day variations in the observatory's equipment, and it appeared to move across the sky in sync with the stars rather than with the sun, suggesting it had an astronomical origin. They also considered whether it might be a signal bouncing off the moon or a satellite, but the signal's characteristics didn't match these possibilities either. The LGM hypothesis became increasingly untenable when Bell Burnell discovered a second pulsating source in a completely different part of the sky. Then a third, then a fourth. The signals all had different periods, ranging from about 1 to 4 seconds, and they came from widely separated locations across the galaxy. It became highly implausible that multiple alien civilizations would all be beaming signals at Earth, using similar technology from different parts of the galaxy. The signals had to be from some natural astronomical phenomenon. The question became, what natural process could produce such regular pulses? Various ideas were considered. Pulsating variable stars were known, but they pulsed with periods of hours or days, not seconds. White dwarfs were proposed, but calculations showed that a white dwarf would break apart if it tried to pulsate or rotate fast enough to produce a 1-second period. The answer came from theoretical predictions about neutron stars. Neutron stars had been predicted theoretically in the 1930s by Walter Baade and Fritz Zwicky shortly after the discovery of the neutron as a particle. They suggested that in a supernova explosion, a star's core might be compressed so severely that protons and electrons would merge to form neutrons, creating an incredibly dense object. Later calculations in the 1960s explored what such an object might look like. If a neutron star retained the angular momentum of its progenitor star's core and also retained and compressed its magnetic field, it would be rotating rapidly and would have an intense magnetic field. Such an object might emit radiation from its magnetic poles, and if those poles weren't aligned with the rotation axis, the radiation would sweep around like a lighthouse beam. Thomas Gold proposed this model shortly after the first pulsars were discovered. He argued that the regular periods were consistent with rotation rather than pulsation, and that neutron stars were the only known objects that could sustain such rapid rotation without flying apart. The model explained not only the regularity of the pulses, but also why the period was gradually increasing. The neutron star was slowing down as it radiated energy away, exactly as Gold's calculations predicted. The definitive confirmation came in late 1968 with the discovery of a pulsar in the Crab Nebula. The PED, Crab Nebula, is the remnant of a supernova that was observed by Chinese astronomers in the year 1054. It's one of the best-studied objects in astronomy, and astronomers had long suspected that it might contain a neutron star at its center, powering the nebula's glow. When a pulsar was discovered at the exact center of the Crab Nebula, with a period of 33 milliseconds, it confirmed the connection between pulsars, neutron stars, and supernovae. PSR B1919+121, the first discovered pulsar, became an object of intense study. Its period of 1.337 seconds made it typical of what are now called normal pulsars, as opposed to the millisecond pulsars discovered later. The pulsar is located about 2,000 light-years from Earth in the constellation Vulpecula. Observations over the decades have shown that its period is gradually increasing by about 13 nanoseconds per day, consistent with the expected spin-down of a rotating neutron star losing energy through radiation. The discovery earned Anthony Hewish a share of the Nobel Prize in Physics in 1974. The prize was awarded for his decisive role in the discovery of pulsars, though, notably, Jocelyn Bell Burnell was not included as a co-recipient. This omission has been controversial. Bell Burnell made the initial observation, recognized that the signal was unusual, followed up on it, and discovered additional pulsars that ruled out the possibility of a single anomaly. Many astronomers and historians of science have argued that she should have shared in the prize. Bell Burnell herself has been gracious about the matter, noting that as a graduate student she was junior in the project, but the scientific community has generally recognized her crucial contribution to the discovery. The discovery of pulsars opened up an entirely new field of observational astronomy. Before 1967, neutron stars were theoretical objects. After the pulsar discoveries, they became real, observable, and studyable. Astronomers could now test theories about extreme states of matter, about general relativity, about stellar evolution, and about supernova explosions by observing pulsars and analyzing their properties. PSR B1919+221 has become iconic not just in astronomy, but in popular culture. The chart recordings of its pulses, showing the regular spikes repeating with such precision, became visual symbols of the discovery. These images appeared in scientific papers, textbooks, and museum displays, Most famously, they appeared on the cover of the album Unknown Pleasures by the post-punk band Joy Division, where the stacked plot of radio pulses became one of the most recognizable album covers in rock music. The pulsar continues to be monitored by radio telescopes around the world. It serves as a calibration source, a way to verify that telescopes are working correctly. Its regular pulses provide a cosmic clock that can be used to study the intervening medium between Earth and the pulsar, revealing information about the distribution of matter in interstellar space. Every observation adds to the decades-long record of this pulsar's behavior, tracking its gradual slowdown and searching for anomalies that might reveal something new about neutron star physics. The story of PSR B9919+21 is ultimately about how unexpected observations can transform our understanding of the universe. Bell Burnell was looking for quasar scintillation and found something completely different. The discovery required careful attention to unusual signals, willingness to follow up on anomalies even when they didn't fit the expected pattern, and the intellectual courage to consider that the universe might contain objects unlike anything previously observed. These qualities remain essential in astronomy today, as observers continue to scan the skies for the next unexpected discovery that might once again expand our knowledge of the cosmos. In the realm of neutron stars, magnetars occupy an extreme position. These objects possess magnetic fields about 1,000 times stronger than typical neutron stars, making them the most magnetic objects known in the universe. A magnetar's magnetic field strength can exceed 1 quadrillion Gauss, or about 100 trillion times Earth's magnetic field. At such strengths, the magnetic field itself becomes a dominant force, capable of distorting atomic structure and affecting the vacuum of space. To understand how strong this is, consider that a regular neutron star's magnetic field is already about 1 trillion Gauss, strong enough to erase every credit card on Earth from a distance halfway to the moon. A magnetar's field is 1,000 times stronger still. If a magnetar was somehow placed at the distance of the moon from Earth, its magnetic field would be lethal to life on our planet. The field would compress atoms themselves, squeezing hydrogen atoms into shapes 200 times narrower than normal. Biological molecules would cease to function. The chemical bonds that hold matter together would be disrupted. Approaching within about 1,000 kilometers of a magnetar would be fatal from the magnetic field effects alone, long before gravitational or radiation effects became significant. The origin of these extreme magnetic fields remains somewhat uncertain. One theory suggests that magnetars form when neutron stars are born from progenitor stars that were rotating extremely rapidly. During the collapse of the star's core, the rapid rotation combined with convection in the ultra-dense matter generates a dynamo effect, amplifying the magnetic field to magnetar strengths. This would be similar to how Earth's magnetic field is generated by convection in its liquid iron outer core, but operating under far more extreme conditions and producing a far stronger result. Another possibility is that magnetars simply form from progenitor stars that already had unusually strong magnetic fields. When the core collapses, the magnetic field is compressed along with everything else, and a strong initial field could become a magnetar strength field after compression. Recent observations have found massive stars with strong magnetic fields that could potentially become magnetars when they eventually explode as supernovae. The star HD 45166, for instance, has been observed to have a magnetic field about 43,000 times stronger than typical for stars of its type, and it's in a stage of evolution that suggests it will eventually explode and leave behind a neutron star that could well be a magnetar. Magnetars reveal themselves through their energetic outbursts. Unlike normal pulsars, which steadily emit radiation powered by their rotation, magnetars experience violent episodes where they suddenly release enormous amounts of energy in the form of X-rays and gamma rays. These bursts happen when the magnetar's crust fractures. The crust of a neutron star is a solid lattice of iron nuclei and other heavy elements, but in a magnetar, the magnetic field is so strong that it stresses the crust, building up tension over time. Eventually, the crust breaks in a starquake, a sudden readjustment that releases magnetic energy. During a magnetar flare, the star's brightness can increase by factors of hundreds or thousands in a fraction of a second. The energy released in these events is staggering. A magnetar called SGR 1806-20 produced a burst on December 27, 2004 that released more energy in 1/10 of a second than the Sun has emitted in the past 100,000 years. The burst was so intense that it affected Earth's upper atmosphere from a distance of 50,000 light-years, compressing the ionosphere and temporarily disrupting radio communications. These starquakes happen because the magnetic field is not static. The intense magnetic field gradually evolves, shifting and reconfiguring as currents flow through the superconducting interior of the neutron star. This evolution stresses the solid crust, which is locked to the magnetic field. When the stress becomes too great, the crust cracks. These cracks can be global events, fractures that run across significant portions of the star's surface. The breaking crust releases stored elastic energy and also allows the magnetic field to reconfigure suddenly, and both processes contribute to the energetic burst. The magnetic fields of magnetars are strong enough to affect the vacuum itself. In quantum field theory, the vacuum isn't truly empty, but filled with virtual particle-antiparticle pairs that constantly appear and disappear. In the presence of an extremely strong magnetic field, these virtual particles can be affected before they annihilate, leading to observable effects. One prediction is magnetic photon splitting, where a single high-energy photon entering a magnetar's magnetic field can split into two lower-energy photons. Another is vacuum birefringence, where the vacuum acts like a birefringent crystal, causing different polarizations of light to travel at slightly different speeds. These exotic quantum effects have been observed in the X-ray emissions from some magnetars, confirming theoretical predictions about how matter and energy behave in such extreme conditions. Magnetars rotate more slowly than typical pulsars. While normal pulsars spin several times per second, or even hundreds of times per second in the case of millisecond pulsars, magnetars typically rotate once every 2 to 10 seconds. This slower rotation is thought to be a consequence of their stronger magnetic fields. The intense magnetic field creates greater magnetic braking, causing young magnetars to spin down more rapidly than normal pulsars. By the time a magnetar is old enough to be detected, its rotation has already slowed substantially. Despite their slower rotation, magnetars are among the most luminous X-ray sources in the galaxy. Their X-ray emission isn't powered primarily by rotation, as it is for normal pulsars, but by the decay of the magnetic field. As the magnetic field gradually weakens over tens of thousands of years, the energy stored in the field is converted into heat, which is radiated away as X-rays. This makes magnetars visible at X-ray wavelengths long after a comparable normal pulsar would have faded from detection. The lifetime of a magnetar as an active object is relatively short on cosmic timescales. The intense magnetic field decays over about 10,000 years, after which the magnetar becomes a normal neutron star, indistinguishable from other neutron stars of similar age, except perhaps for having a slightly stronger magnetic field than average. This means that magnetars represent a brief, violent phase in the life of certain neutron stars. The galaxy has likely produced many magnetars over its history, but most have already faded and are no longer identifiable as magnetars. As of the most recent surveys, only about 24 confirmed magnetars have been identified. This small number partly reflects their short active lifetime. There simply aren't many magnetars active at any given time, and partly reflects the difficulty of identifying them. A magnetar that isn't currently bursting can be hard to distinguish from a regular neutron star. They're identified primarily through their X-ray emission patterns and through bursts when they occur. When a previously unknown source suddenly begins emitting intense X-ray bursts, astronomers investigate to determine if it might be a newly active magnetar. Is somewhat fuzzy, reflecting the continuous nature of stellar properties rather than sharp dividing lines. The study of magnetars continues to reveal new aspects of physics under extreme conditions. Each burst provides data about how matter behaves when magnetic fields become comparable to the binding forces that hold atoms together. Each observation of a magnetar's X-ray spectrum tests theoretical predictions about quantum electrodynamics in strong fields. These objects push the boundaries of our understanding precisely because they create conditions that simply don't exist anywhere else in the accessible universe. White dwarfs can also become zombie stars through a different mechanism. Instead of radiating energy from rotational or magnetic reserves like neutron stars, some white dwarfs extend their active existence by drawing material from companion stars. These accreting white dwarfs exist in binary systems where gravitational interactions allow them to strip matter from their partners. The stolen material accumulates on the white dwarf's surface until conditions become extreme enough to trigger thermonuclear fusion. The resulting explosion is called a nova, and the cycle can repeat over timescales ranging from years to millennia. The process begins with orbital evolution. Many stars form in binary systems, two stars orbiting around their common center of mass. When one star evolves off the main sequence and becomes a white dwarf, it doesn't necessarily cease interacting with its companion. If the two stars are close enough, the white dwarf's gravity can pull material from the companion's outer layers. This material doesn't fall directly onto the white dwarf. Instead, it forms an accretion disk, a spiral of gas that gradually moves inward, heating through friction until it reaches temperatures of tens of thousands of degrees. The material in this accretion disk is primarily hydrogen, the leftover fuel from the companion star's outer envelope. As it spirals inward, it eventually reaches the white dwarf's surface and settles into a thin layer. This accreted hydrogen is compressed by the white dwarf's intense gravity, becoming denser and hotter. But because the white dwarf is composed of degenerate matter, the material can't expand to relieve this pressure. The hydrogen layer becomes increasingly unstable, its temperature rising until it reaches the ignition point for fusion. When the temperature at the base of the accreted layer reaches around 20 million degrees, fusion ignites. But this isn't the controlled fusion that occurs in the cores of main sequence stars. This is a runaway thermonuclear explosion. The entire accreted layer fuses essentially instantaneously, releasing enormous energy. The white dwarf's surface explodes outward, ejecting the accumulated material at speeds of thousands of kilometers per second. The system's brightness increases by factors of thousands to tens of thousands, creating what observers see as a nova, a new star appearing in the sky where none was visible before. After the explosion, the white dwarf is still intact. The detonation occurs only in the accreted layer, not in the white dwarf's core. Once the explosion ejects the accumulated hydrogen, the white dwarf continues pulling material from its companion, and the cycle begins again. The time between Explosions depends on how fast material accumulates, which in turn depends on the orbital configuration and the nature of the companion star. Some binary systems produce recurrent novae, explosions that repeat on timescales short enough to have been observed multiple times in recorded history. The system RS Ophiuchi consists of a white dwarf and a red giant star in close orbit. The white dwarf has been observed to erupt about 6 times in the 20th century, and once more in 2006 and again in 2021. Each eruption follows a similar pattern. The system brightens from magnitude 11, too faint to see without a telescope, to around magnitude 5, easily visible to the naked eye over the course of about a day. It then fades back to its quiescent brightness over several weeks. The white dwarf in RS Ophiuchi is thought to be extremely massive, possibly approaching the Chandrasekhar limit of about 1.4 solar masses. This is the maximum mass a white dwarf can have while being supported by electron degeneracy pressure. Above this limit, the pressure isn't sufficient to prevent further collapse, and the white dwarf will either collapse to a neutron star or, more commonly, detonate completely in what's called a Type Ia supernova. The question of whether accreting white dwarfs in systems like RS Ophiuchi are gaining or losing mass over time is a subject of ongoing research. Each nova explosion ejects material, but some of that material is freshly fused elements rather than the original accreted hydrogen. If the white dwarf ejects more mass than it accretes between explosions, it will gradually lose mass. If it retains more than it ejects, it will gradually gain mass and could eventually reach the Chandrasekhar limit. Observations of RS Ophiuchi suggest its white dwarf may indeed be growing, though the question remains uncertain. Another recurrent nova, T Pyxidis, has been studied extensively. This system has erupted approximately every 20 years since its discovery, with recorded outbursts in 1890, 1902, 1920, 1944, and 1967. The system was then expected to erupt again around the late 1980s or early 1990s, but it didn't. Observers watched and waited, and the nova finally erupted again in 2011, having been overdue by more than 2 decades. This long gap raised questions about whether the accumulation rate had changed or whether some aspect of the system's behavior was different from previous cycles. T Pyxidis is located about 6,000 light-years from Earth in the constellation Pyxis. Observations with the Hubble Space Telescope revealed that previous nova explosions from this system had created shells of ejected material surrounding the binary. These shells consist of thousands of individual gaseous blobs, each expanding outward at high speed. The structure provides a fossil record of past eruptions, allowing astronomers to study the history of the system's activity. Not all novae are recurrent on human timescales. Classical novae are single observed explosions in systems where the recurrence time is likely thousands to hundreds of thousands of years. These systems may still repeat, but the time between explosions is so long that humanity is unlikely to observe more than one eruption from any given system. The distinction between recurrent and classical novae is somewhat arbitrary, based on whether humans have lived long enough to see multiple eruptions rather than on any fundamental physical difference. The companion stars in these systems can be main sequence stars like the Sun, subgiants that have begun to evolve off the main sequence, or red giants in advanced stages of evolution. The orbital periods range from hours to years depending on the separation between the stars. Systems with very short orbital periods, where the stars orbit each other in just a few hours, tend to have higher mass transfer rates and shorter recurrence times. Systems with longer periods have lower mass transfer rates and longer times between eruptions. The Chandrasekhar limit plays a critical role in the ultimate fate of accreting white dwarfs. This limit, calculated by Indian astrophysicist Subramanian Chandrasekhar in the 1930s, represents the point where electron degeneracy pressure can no longer support the white dwarf against gravity. The exact value depends on the composition of the white dwarf, but for carbon-oxygen white dwarfs, which are the most common type, the limit is about 1.44 solar masses. If a white dwarf manages to accrete enough material to reach this limit, the consequences are dramatic. The entire white dwarf becomes unstable. Carbon fusion ignites not just in an outer layer, but throughout the star. The fusion spreads through the star at supersonic speeds in a process called a detonation wave. In less than a second, the entire white dwarf burns to iron peak elements, releasing so much energy that the star is completely destroyed. There's no remnant left behind, no neutron star or black hole. The white dwarf is converted entirely into kinetic energy and newly synthesized elements that are ejected into space. This is a Type Ia supernova, one of the most important classes of stellar explosions in astronomy. Type Ia supernovae are remarkably consistent in their peak brightness, making them useful as standard candles for measuring cosmic distances. Observations of distant Type Ia supernovae in the late 1990s revealed that the expansion of the universe is accelerating, a discovery that earned the Nobel Prize in Physics in 2011 and changed our understanding of cosmology. The exact mechanism that triggers Type Ia supernovae remains uncertain. The classical scenario involves a white dwarf accreting material from a companion until it reaches the Chandrasekhar limit, but observations have revealed complications. Some Type Ia supernovae show properties that are difficult to explain with this single degenerate scenario. An alternative mechanism involves two white dwarfs in a binary system that spiral together and merge due to gravitational wave emission. If their combined mass exceeds the Chandrasekhar limit, the merger could trigger a supernova explosion. Recent discoveries have found white dwarf binary systems that will merge in the relatively near future on cosmic timescales. One such system, designated WDJ 18158.67plan31940294, consists of two white dwarfs with a combined mass of 1.55 solar masses. The stars will merge in about 23 billion years, likely producing a Type Ia supernova. This system is located only 49 parsecs from Earth, about 160 light-years, making it one of the closest such systems known. When it eventually explodes, it will briefly become brighter than any other star in the sky, though this won't happen for an immensely long time. For now, accreting white dwarfs in nova systems represent a more sedate form of zombie star behavior. They're not producing the regular pulses of radiation that characterize pulsars. They're not exhibiting the violent magnetic outbursts of magnetars. Instead, they're quietly cannibalizing their companions, accumulating mass over years or decades until another thermonuclear explosion temporarily revives their luminosity. Between explosions, these systems are dim and unremarkable, detectable only through careful observation. But each nova eruption is a reminder that these white dwarfs remain active participants in their binary systems, drawing energy not from their own reserves, but from the ongoing sacrifice of their companion stars. The universe operates on timescales that resist everyday comprehension. When we think about zombie stars, whether neutron stars or white dwarfs, we're considering objects that will persist long after the current generation of normal stars has exhausted its fuel and faded. A neutron star formed today will still exist, essentially unchanged, when the sun has become a white dwarf and begun its own slow fade into darkness. The white dwarf that will eventually form from the Sun's core will cool over trillions of years, longer than the current age of the universe by factors of hundreds. This persistence gives zombie stars a particular quality. They're not actively changing in the dramatic way that living stars change. A massive star progresses from hydrogen burning to helium burning to carbon burning and onward through the fusion chain in a few million years. But a neutron star, once formed, simply exists. It spins, it cools, its magnetic field gradually weakens, but the fundamental object remains. It's reached an equilibrium state that doesn't require ongoing nuclear fusion to maintain. The same is true for white dwarfs in isolation. Once formed, they begin cooling at a rate determined by their surface area and temperature. The cooling rate follows predictable curves that have been calculated theoretically and confirmed observationally. A white dwarf doesn't suddenly decide to reignite fusion or undergo some unexpected transformation. It simply radiates away its heat, gradually cooling from white-hot to red, to eventually becoming too dim to see, a process that takes longer than the current age of the cosmos. Even accreting white dwarfs in binary systems, despite their nova eruptions, are fundamentally stable over long timescales. Each nova explosion is dramatic but brief, lasting weeks or perhaps months before the system returns to its quiescent state. The cycle repeats, but between eruptions, the white dwarf sits unchanged, slowly accumulating material for the next explosion. The timescale between eruptions, whether years or millennia, is still short compared to the age of the white dwarf itself, which may have been cooling for billions of years before entering the binary interaction phase. Consider the Crab Nebula pulsar. This neutron star was formed in 1054 during a supernova explosion observed by Chinese astronomers. Nearly 1,000 years have passed, and the pulsar is still active, still spinning 30 times per second, still emitting radiation across the electromagnetic spectrum. It's slowing down, losing about 15 milliseconds per year from its rotation period, but at this rate it will take millions of years before it slows enough to become undetectable. The neutron star itself will persist for vastly longer, essentially forever by human standards. The magnetic field of the Crab pulsar will eventually decay to the point where it no longer produces observable radiation. The star will become what astronomers call a dead pulsar, or a quiet neutron star. But it will still exist. It will still be spinning, though more slowly. It will still be incredibly dense, still supported by neutron degeneracy pressure. It will have simply entered a passive phase where it's no longer detectable through electromagnetic emission. The galaxy likely contains vast numbers of these quiet neutron stars, remnants of stars that exploded millions or billions of years ago, but are now too faint to observe. White dwarfs will undergo a similar transition. After trillions of years of cooling, a white dwarf will reach temperatures low enough that it no longer emits visible light. It becomes a black dwarf, a cold remnant composed of crystallized carbon and oxygen, invisible against the darkness of space. These objects don't yet exist in our universe because the universe is only about 14 billion years old, far too young for any white dwarf to have cooled completely. The first black dwarfs won't appear for thousands of billions of years, but when they do, they'll persist essentially forever, monuments to stars that died when the universe was young. This raises a perspective worth considering. The stars we see in the night sky, the ones that have inspired humanity throughout history, are temporary. They're consuming fuel, evolving, moving toward eventual death. But the remnants they leave behind, the zombie stars, are permanent. In the far future of the universe, when star formation has ceased because all the available gas has been used up, the cosmos will be populated primarily by stellar remnants. White dwarfs, neutron stars, and black holes will be the dominant objects, outnumbering active stars by enormous factors. In this sense, zombie stars represent the ultimate fate of normal matter in the universe. Barring proton decay or other exotic physics, these objects will persist essentially unchanged for durations that make even the current age of the universe seem like a brief moment. They're not just the end state of stellar evolution. They're the future, the form that most matter will eventually take once the era of star formation and active stellar life has ended. But that future is unimaginably distant. For now, zombie stars coexist with active stars, providing astronomers with laboratories for studying extreme physics. Every observation of a pulsar helps refine our understanding of how matter behaves at nuclear densities. Every nova eruption from an accreting white dwarf provides data about thermonuclear fusion under degenerate conditions. Every magnetar burst tests our theories about magnetic field physics at strengths far beyond anything achievable in terrestrial laboratories. These objects bridge the gap between theoretical physics and observational reality. Many aspects of their behavior were predicted decades before they were observed. Neutron stars were theoretically proposed in the 1930s, but weren't detected until the pulsar discovery in 1967. The properties of white dwarfs were calculated mathematically before observations confirmed those calculations. The consistency between theory and observation demonstrates that our understanding of physics, even in extreme conditions, is fundamentally sound. Yet, mysteries remain. The equation of state of nuclear matter at neutron star densities is still uncertain. Observations of neutron star masses and radii help constrain the possibilities, but multiple theoretical models remain consistent with current data. The interior composition of neutron stars, whether they contain exotic phases of matter like quark-gluon plasma or hyperons, is still debated. The precise mechanism that triggers type Ia supernovae, whether single degenerate accretion or double degenerate merger or some combination, is still being investigated. Each new observation has the potential to resolve these questions or to raise new ones. The detection of gravitational waves from neutron star mergers in 2017 opened an entirely new window for studying these objects. The simultaneous observation of electromagnetic and gravitational wave signals from the same event allowed astronomers to probe neutron star properties in ways that weren't previously possible. Future observations with more sensitive gravitational wave detectors will provide even more detailed information. For now, zombie stars continue their existence, spinning in darkness, cooling gradually, occasionally revealing themselves through bursts of radiation or gravitational effects on companion stars. They're reminders that stellar death isn't the end of astronomical interest, but rather the beginning of a different kind of existence, one characterized by stability, persistence, and physics at the limits of what the universe allows. They're the universe's way of preserving the products of stellar evolution, keeping them intact for timescales that dwarf human comprehension. Among the pulsar population, millisecond pulsars represent a peculiar subclass. These neutron stars spin extraordinarily fast, completing hundreds of rotations per second. The fastest confirmed millisecond pulsar, PSR J174824446 AD, rotates 716 times per second. At this rate, a point on the star's equator moves at about 1/4 the speed of light. If the star was spinning even slightly faster, centrifugal force would overcome gravity and tear it apart. The existence of these rapid rotators initially puzzled astronomers. Neutron stars are born spinning rapidly when they form in supernova explosions, typically making tens of rotations per second. but they spin down over time as they emit radiation, gradually slowing until they become too faint to detect. A typical pulsar might remain active for 10 million years or so before slowing enough to drop below the detection threshold. After that, it continues to exist as a neutron star, but it's no longer observable as a pulsar. Millisecond pulsars, despite spinning far faster than young pulsars, are actually old. This seems contradictory until you understand the mechanism that creates them. These objects are recycled pulsars, neutron stars that have been spun back up after initially spinning down. The mechanism for this spin-up is accretion from a binary companion. Material falling onto a neutron star from a companion star carries angular momentum. As this material spirals onto the neutron star, it transfers its angular momentum, causing the neutron star to spin faster. This process requires specific conditions. The neutron star must be in a binary system with a companion that's close enough to transfer mass, but not so close that the system was disrupted during the supernova that created the neutron star. The mass transfer must persist for long enough to spin the neutron star up to millisecond periods, which requires millions to tens of millions of years of accretion. During this time, the system appears as an X-ray binary, with the neutron star emitting intense X-rays as material from the accretion disk crashes onto its surface. Eventually, the companion star exhausts whatever material it was transferring, and the accretion ceases. At this point, the rapidly rotating neutron star emerges as a millisecond pulsar. Many millisecond pulsars have white dwarf companions, the remnants of the stars that originally donated mass to spin them up. The white dwarfs are typically low in mass, having lost much of their material to the neutron star. Some have masses as low as 0.2 solar masses, far less than the typical white dwarf mass of around 0.6 solar masses. The orbital periods of millisecond pulsar binary systems vary widely. Some have periods of just a few hours, while others have periods of months or even years. The period depends on how the binary system evolved, which in turn depends on the masses of both stars and the timing of various evolutionary stages. Short-period systems tend to have low-mass white dwarf companions and circular orbits. Longer-period systems can have more massive companions and show more eccentricity in their orbits. Some millisecond pulsars are isolated, not in binary systems. These solitary millisecond pulsars, often called black widow pulsars or redback pulsars, depending on their companion mass, if they were once in binaries, have particularly interesting histories. The leading explanation for their isolation is that they evaporated their companions. The intense radiation from the millisecond pulsar, particularly if it was oriented such that the pulsar beams swept across the companion star, could have heated and stripped material from the companion. Over time, this ablation could have completely destroyed a low-mass companion, leaving the millisecond pulsar alone. Black widow pulsars are named after the spider species, where females sometimes consume their mates. In these systems, the millisecond pulsar is actively destroying its companion, which is typically a very low-mass star or brown dwarf. The pulsar's radiation heats one side of the companion to thousands of degrees, causing material to evaporate away. Some black widow systems show eclipses, where the pulsar signal disappears for part of each orbit as it passes behind the evaporating material from the companion. These eclipses vary from orbit to orbit depending on how much material is in the line of sight, providing real-time observations of the ablation process. The spin stability of millisecond pulsars is remarkable. Their rotation periods are so consistent that they rival atomic clocks in precision. The most stable millisecond pulsars change their periods by only nanoseconds per year. This stability makes them useful as cosmic clocks. Arrays of millisecond pulsars distributed across the sky are being monitored by astronomers to search for gravitational waves at very low frequencies, much lower than ground-based detectors like LIGO can observe. The concept is straightforward but technically demanding. Gravitational waves passing through the galaxy will slightly stretch and compress space, affecting the distance between Earth and distant pulsars. These distance changes, though incredibly tiny, alter the arrival times of pulsar pulses by nanoseconds. By precisely monitoring the timing of dozens of millisecond pulsars simultaneously, astronomers can detect correlated timing variations that might indicate passing gravitational waves. This technique, called pulsar timing arrays, is sensitive to gravitational waves with periods of months to years, complementing the seconds to minutes range that LIGO observes. In 2023, multiple pulsar timing array collaborations announced evidence for a gravitational wave background, a bath of gravitational waves filling the universe. This background is thought to arise from countless supermassive black hole binaries throughout cosmic history, each pair producing gravitational waves as they spiral together. The signal is still being confirmed and characterized, but if validated, it would represent a major discovery in gravitational wave astronomy, opening observations to entirely new wavelength regime. Millisecond pulsars also provide precise tests of general relativity. The binary pulsar PSR J0737-3URP39 is particularly notable because it's a double neutron star system where both neutron stars are observable as pulsars. This makes it an extraordinary laboratory for relativistic effects. Astronomers can measure the masses of both neutron stars with high precision, track how the orbit evolves due to gravitational wave emission, observe how the pulses are affected by the gravitational field of the companion, and test predictions about spacetime in strong gravitational fields. One of the effects observable in such systems is the Shapiro delay, where pulsar signals are delayed as they pass through the gravitational field of the companion star. The size of the delay depends on the companion's mass and the geometry of the orbit. By measuring the Shapiro delay, astronomers can determine the companion's mass independently of orbital dynamics. In systems where both stars are pulsars, this provides a redundant check on the mass measurements and tests whether general relativity correctly predicts the behavior of light in gravitational fields. Another observable effect is orbital precession, where the orbit itself rotates over time. In Newtonian gravity, orbits are fixed ellipses, but general relativity predicts that orbits precess, with the point of closest approach shifting position with each orbit. This effect is tiny for most solar system objects, but becomes measurable in compact binary systems where orbital velocities approach significant fractions of light speed. The rate of precession depends on the masses of both objects and tests whether space-time is curved in the way general relativity predicts. The rotation rate of millisecond pulsars also tells us about the equation of state of nuclear matter. A neutron star can only spin so fast before centrifugal force at its equator exceeds gravity. The maximum spin rate depends on the mass and radius of the neutron star, which in turn depend on how matter behaves at nuclear densities. By observing the fastest spinning pulsars, astronomers constrain the possible equations of state, ruling out models that would allow faster rotation than observed or predict instability at slower rates than the fastest pulsars achieve. PSR J1774824446 the fastest known pulsar, spins at 716 times per second. This means its period is only 1.4 milliseconds. At this rotation rate, the star's equator is moving at about 24% of light speed, and the centrifugal acceleration nearly balances gravitational acceleration. The star is almost at its breakup limit. If it were any more massive or spinning any faster, it would become unstable. The fact that it exists at all tells us that neutron star matter must be stiff enough to support this rapid rotation without deforming catastrophically. Interestingly, no pulsars have been found spinning significantly faster than about 716 times per second, despite searches that would easily detect faster rotation if it existed. This suggests that something prevents neutron stars from spinning faster, either because the accretion process that spins them up becomes less efficient at higher rates or because additional physics comes into play near the breakup limit. Gravitational wave emission might drain angular momentum from the fastest rotating neutron stars, preventing them from spinning up further. Or perhaps the equation of state changes at extreme rotation rates in ways that limit maximum spin. Millisecond pulsars represent a second life for neutron stars. After forming in a supernova and spending millions of years as a young pulsar, slowly spinning down and fading from view, they can be resurrected through accretion. The theft of angular momentum from a companion star returns them to activity, allowing them to emit detectable radiation for billions of years. In this way, they're among the longest-lived, active zombie stars, persisting as observable objects for timescales that exceed the ages of most stars in the galaxy. They're cosmic phoenixes, rising from electromagnetic death through gravitational cannibalism. The interior of a neutron star is hidden from direct observation, but theoretical models combined with observational constraints have revealed likely structure. These objects are not uniform spheres of neutron matter. Instead, they're thought to have a layered structure with composition and density varying from the surface to the core. Each layer represents a different phase of matter, some familiar and some utterly exotic. The outermost layer is a solid crust composed primarily of iron nuclei and electrons. Despite the extreme densities, this outer crust maintains a crystalline structure similar to metals on Earth, but compressed to far higher densities. The nuclei are packed tightly together, but they still maintain their identity as individual nuclei. Electrons move freely between them, making the crust an excellent electrical conductor. The temperature of this layer varies depending on the neutron star's age, ranging from millions of degrees for young neutron stars to merely hundreds of thousands of degrees for older ones. As you descend deeper into the crust, the density increases and the composition changes. The nuclei become more neutron-rich, incorporating more neutrons than would be stable under normal conditions. These neutron-rich nuclei exist only because the intense pressure prevents them from decaying. At depths where the density reaches about 1,000,000 grams per cubic centimeter, free neutrons begin to appear, no longer bound within nuclei, but existing as a sea of neutrons interpenetrating the lattice of nuclei. Deeper still, around densities of 10 million to 100 million grams per cubic centimeter, the nature of matter becomes truly exotic. At these densities, spherical nuclei become energetically unfavorable. The nuclei deform, elongating into rod-like structures or flattening into plates. These phases are collectively called nuclear pasta, with specific shapes given names like nuclear spaghetti for rod-like structures, nuclear lasagna for plate-like structures, and nuclear gnocchi for more complex clustered shapes. The nuclear pasta phases exist because of competition between nuclear forces, which try to keep nucleons together, and Coulomb forces from the protons, which push nuclei apart. At extreme densities, nuclei can lower their energy by adopting non-spherical shapes that minimize surface energy while accommodating the repulsive forces. These pasta phases are thought to exist in a layer a few hundred meters thick inside the neutron star, though the exact extent depends on the star's mass and the details of nuclear physics. Below the pasta layer lies the outer core, where densities exceed the density of atomic nuclei. At this point, the concept of individual nuclei breaks down completely. The matter exists as a uniform fluid of neutrons, with a small admixture of protons and electrons. This neutron fluid is predicted to be a superfluid, a quantum state where the neutrons flow without viscosity. Superfluidity occurs when particles form Cooper pairs, bound states that can move through the medium without scattering. This is similar to superconductivity in metals, where electrons form pairs that conduct electricity with zero resistance. The protons in the outer core, though less numerous than neutrons, are also predicted to be superconducting. This means electric currents can flow through the proton component without resistance, generating magnetic fields that can persist for millions of years without decaying. This superconductivity may be responsible for the intense magnetic fields observed in pulsars and magnetars, with currents flowing in the superconducting proton layer, generating fields that thread through the star and extend into the surrounding space. The inner core, where densities are highest, is the most uncertain region. At densities several times nuclear density, new forms of matter may appear. One possibility is that neutrons break down into their constituent quarks, creating a quark-gluon plasma similar to the state of matter that existed microseconds after the Big Bang. In this phase, quarks move freely throughout the core rather than being confined within individual neutrons. The transition from neutron matter to quark matter might be sharp, with a distinct boundary, or gradual, with an intermediate mixed phase. Another possibility involves the appearance of hyperons, particles that contain strange quarks. In normal matter, all particles are made from up and down quarks. But at high densities, it becomes energetically favorable to create particles containing strange quarks as well. These hyperons would be mixed in with the neutrons, affecting the pressure and changing the maximum mass a neutron star can support. The presence of hyperons tends to soften the equation of state, reducing the maximum possible neutron star mass. More exotic possibilities include kaon condensates, where meson particles condense into a quantum state that affects the equation of state, or even more unusual forms of matter predicted by various extensions of the standard model of particle physics. Each possibility makes different predictions about observable properties like maximum mass, radius, and cooling rates. Comparing these predictions to observations helps rule out some models and constrain others. The cooling history of a neutron star depends on its interior composition. Neutron stars are born incredibly hot, with internal temperatures exceeding billions of degrees. This heat is left over from the gravitational collapse and from the energy released during neutron formation. The star cools primarily through neutrino emission for the first 10,000 years or so. Neutrinos, being weakly interacting particles, escape directly from the interior, carrying energy away more efficiently than photons, which must diffuse through the dense matter. Different interior compositions affect the cooling rate because they enable different neutrino production mechanisms. The presence of exotic matter, like hyperons or quark matter, opens up additional pathways for neutrino emission, causing the star to cool faster. By observing the temperatures of neutron stars of known age, astronomers can constrain which forms of matter are likely present in the cores. Young neutron stars that are cooler than expected might contain exotic matter, while those that are warmer might have simpler compositions dominated by neutrons and protons. After the initial rapid cooling phase, photon emission from the surface takes over as the dominant cooling mechanism. This thermal cooling continues for billions of years, gradually lowering the neutron star's temperature. The oldest neutron stars in the galaxy have likely cooled to temperatures of only a few 100,000 degrees, though they remain far hotter than any normal star's surface. These ancient neutron stars are difficult to observe because they're so faint, but space-based X-ray telescopes can detect them, providing information about the oldest generation of neutron stars in our region of the galaxy. The superfluid and superconducting properties of the interior affect observable phenomena like pulsar glitches. A glitch occurs when the crust of the neutron star suddenly speeds up, causing the pulsar period to decrease abruptly. Glitches happen because the superfluid interior can rotate faster than the crust. The crust slows down due to magnetic braking, but the superfluid interior continues spinning at a higher rate because it's not coupled to the magnetic field. Eventually, the difference in rotation rates becomes large enough that the superfluid couples to the crust through some mechanism, perhaps involving quantized vortices in the superfluid. When this coupling occurs, angular momentum transfers from the interior to the crust, causing the crust to suddenly spin up. The Crab pulsar has been observed to glitch multiple times. Each glitch causes the period to decrease by a few microseconds, a tiny change but easily measurable given the precision with which pulsar periods can be determined. After a glitch, the pulsar gradually returns toward its pre-glitch spin-down rate as the crust and interior gradually recouple. The details of this recovery process provide information about the coupling between the crust and interior, helping to constrain models of superfluid behavior. The magnetic field structure inside a neutron star also depends on the interior composition. If the core is superconducting, magnetic field lines can only penetrate it in quantized flux tubes, each carrying a fixed amount of magnetic flux. This quantization affects how the magnetic field evolves over time. In normal matter, magnetic fields can diffuse and rearrange freely. But in a superconductor, the flux tubes are pinned and can only move through discrete jumps. This could explain why neutron star magnetic fields are so stable, persisting with relatively little decay for millions of years. Magnetars, with their extreme magnetic fields, pose particular questions about interior structure. Some theories suggest that magnetar fields are generated and sustained by a dynamo mechanism operating in a differentially rotating core. If the inner core rotates at a different rate than the outer layers, the differential rotation can twist and amplify magnetic field lines, generating the intense fields observed. This would require the interior to have specific properties that allow different layers to rotate semi-independently, possibly involving exotic phases of matter with unusual viscosity properties. The equation of state of neutron star matter determines the mass-radius relationship. A stiff equation of state, where pressure increases rapidly with density, produces larger neutron stars for a given mass. A soft equation of state produces smaller, more compact neutron stars. Observations of neutron star masses and radii from X-ray timing and gravitational wave observations are gradually constraining the equation of state, ruling out extreme soft or extreme stiff models and pointing toward intermediate possibilities. The maximum mass a neutron star can have before collapsing to a black hole is one of the key predictions of the equation of state. Current observations suggest the maximum mass is around 2 to 2.5 solar masses, though the exact value remains uncertain. Neutron stars with masses close to this limit would have the highest central densities, increasing the likelihood that exotic phases of matter exist in their cores. The heaviest confirmed neutron star, PSR J0348+0432, has a mass of about 2.01 solar masses, very close to the theoretical maximum predicted by some equations of state. Understanding neutron star interiors requires combining theoretical nuclear physics with astrophysical observations. No terrestrial experiment can recreate the densities and pressures that exist in neutron star cores. The only laboratory where these conditions occur naturally is inside neutron stars themselves. Every observation that constrains neutron star properties helps refine our understanding of how matter behaves under the most extreme conditions short of black hole formation. These zombie stars, dead in the sense that they no longer burn nuclear fuel, remain invaluable sources of information about fundamental physics. When two neutron stars orbit each other, they emit gravitational waves, ripples in space-time, that carry energy away from the system. This energy loss causes the orbit to decay, bringing the stars gradually closer together. Over millions or billions of years, the orbit shrinks until the stars are only a few hundred kilometers apart, orbiting each other hundreds of times per second. At this point, the orbital decay accelerates dramatically. The gravitational wave emission increases as the stars approach, and within minutes, the neutron stars spiral together and merge. The merger of two neutron stars is one of the most energetic events in the universe short of a supernova. The collision releases energy comparable to 100 supernovae happening simultaneously, most of it carried away by gravitational waves. The neutron stars don't simply crash into each other and stop. Instead, they spiral inward, their shapes distorting as tidal forces become extreme. The orbital period in the final seconds before merger is measured in milliseconds, with the stars orbiting around their common center of mass hundreds of times per second. On August 17, 2017, the LIGO and Virgo gravitational wave detectors observed ripples from a neutron star merger, an event designated GW17817. The signal lasted about 100 seconds, sweeping up in frequency from 24 Hz to a peak around 1 kHz as the stars spiraled together. About 2 seconds after the gravitational wave signal ended, the Fermi and Integral space telescopes detected a burst of gamma rays from the same direction, confirming that the merger had occurred and identifying its position in the sky. Within hours, telescopes around the world and in space began observing the location in various wavelengths. Optical telescopes detected a new point of light, the first optical observation of a gravitational wave source. This optical and infrared emission, called a kilonova, arose from radioactive decay of heavy elements synthesized during the merger. The observations confirmed theoretical predictions that neutron star mergers are major sites of heavy element production in the universe. The process of element synthesis during a merger is violent and complex. When the neutron stars collide, some of their matter is ejected at high speeds, forming expanding clouds around the merger site. This ejected material is extremely neutron-rich, far more so than matter in any other cosmic environment. The excess neutrons are quickly captured by nuclei in a process called rapid neutron capture, or R process nucleosynthesis. In the R process, atomic nuclei absorb neutron after neutron, growing heavier with each capture. The process is so rapid that nuclei don't have time to beta decay between neutron captures, allowing them to climb far up the periodic table. Elements like gold, platinum, uranium, and thorium are produced through R process nucleosynthesis. These heavy elements cannot be made in normal stars because stars don't provide the extreme neutron fluxes necessary. Neutron star mergers and possibly some types of supernovae are the primary cosmic factories for elements heavier than iron. The radioactive decay of these newly synthesized elements powers the kilonova emission. Elements produced in the R process are highly unstable, with half-lives ranging from seconds to days. As they decay towards stability, they release energy in the form of radiation. This radiation heats the expanding material, causing it to glow. Initially, the kilonova is bright at ultraviolet and blue wavelengths, but as it expands and cools over days and weeks, the emission shifts to longer wavelengths, peaking in the red and infrared. Observations of the kilonova from GW170817 provided the first direct evidence that neutron star mergers produce heavy elements. Spectroscopic analysis of the kilonova light showed signatures consistent with the presence of heavy elements. Estimates suggest that this single merger produced several Earth masses worth of gold and platinum, along with comparable amounts of other heavy elements. When this material eventually mixes into interstellar gas clouds, it will enrich future generations of stars and planets with heavy elements. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors all originated in neutron star mergers that occurred billions of years ago, perhaps in the molecular cloud that eventually collapsed to form the Sun and solar system. Every gold atom in your body was forged in the violent collision of two zombie stars, then scattered into space, mixed with other material, and eventually incorporated into the material that formed Earth. The connection between these extreme cosmic events and the mundane matter around us illustrates how intimately connected we are to the most violent processes in the universe. The fate of the merged object depends on its total mass. If the combined mass is below about 2.5 solar masses, the result is a more massive neutron star. This merger remnant is extremely hot and rotating rapidly, typically stabilized temporarily by centrifugal support and thermal pressure. Over time, as it cools and loses angular momentum through gravitational wave emission, it may undergo further evolution. If the mass is above the maximum supported by neutron degeneracy pressure, even accounting for rotation and temperature, the object will collapse to a black hole within seconds to hours of the merger. In the case of GW170817, the evidence suggests the merger initially formed a massive neutron star that likely collapsed to a black hole within seconds. This is inferred from the gamma-ray burst detected shortly after the merger, which is thought to require a black hole to power it. The brief delay between the gravitational wave signal and the gamma-ray burst suggests the system spent a short time as a hypermassive neutron star before collapsing, allowing time for a jet of material to form and break through the surrounding debris, producing the gamma-ray emission observed. Gravitational waves from neutron star mergers carry information about the equation of state of nuclear matter. The gravitational wave signal in the final moments before merger is affected by how easily the neutron stars deform under tidal forces. A neutron star with a stiff equation of state resists tidal deformation more than one with a soft equation of state. This tidal deformability leaves an imprint on the gravitational wave signal that can be measured if the signal-to-noise ratio is high enough. Analysis of GW170817's gravitational wave signal provided constraints on tidal deformability, which in turn constrains the equation of state. The results favor intermediate equations of state, ruling out extremely soft models that would make neutron stars very compact and extremely stiff models that would make them large and easily deformed. Combined with observations of neutron star masses from pulsar timing and X-ray observations of neutron star radii, these gravitational wave constraints are helping to narrow down the properties of ultra-dense matter. Future observations of neutron star mergers will provide additional constraints. LIGO and Virgo, along with the Kagra detector in Japan, and eventually LIGO India, will observe many more mergers as they reach their design sensitivity. Statistical analysis of multiple events will allow more precise measurements of the equation of state than possible from a single event. The next generation of gravitational wave detectors, including Einstein Telescope in Europe and Cosmic Explorer in the United States, will observe mergers out to cosmological distances, potentially detecting hundreds or thousands of events per year. Each merger observation potentially includes electromagnetic counterparts, kilonovae in optical and infrared, gamma-ray bursts, X-ray afterglows, and radio emission as the merger debris interacts with surrounding material. Multi-wavelength observations provide complementary information about the merger environment, the properties of the neutron stars, and the physics of element synthesis and jet formation. The field of multi-messenger astronomy, combining gravitational waves with electromagnetic observations, has opened new ways to study these systems. Neutron star mergers also provide an independent way to measure cosmic expansion rates. The gravitational wave signal from a merger directly measures the distance to the event through the amplitude of the waves. The electromagnetic counterpart, if it includes optical spectroscopy of the host galaxy, provides the redshift, which measures how much the universe has expanded since the light was emitted. Distance plus redshift allows calculation of the Hubble constant, the rate of cosmic expansion. Measurements from GW1770817 yielded a Hubble constant value that helped refine cosmological parameters, though with larger uncertainty than measurements from other methods. As more mergers are observed, this technique will become more precise. The advantage of using gravitational waves is that they provide a direct distance measurement that doesn't depend on the cosmic distance ladder, the chain of intermediate distance measurements that other techniques require. This independence makes gravitational wave measurements valuable for checking systematic errors in other methods and for resolving discrepancies between different techniques that have emerged in recent years. Neutron star mergers represent a late chapter in the lives of zombie stars. The neutron stars themselves were formed from supernovae millions or billions of years earlier. They've existed as compact remnants throughout most of their history, gradually spiraling together due to gravitational wave emission. The merger lasts only seconds, but it's the culmination of eons of orbital decay. And the result, whether a more massive neutron star or a black hole, represents yet another transformation, another step in the life cycle of stellar remnants. The ejected material from mergers, enriched with heavy elements, eventually mixes into the interstellar medium and participates in future star formation. Some of it will become part of planetary systems, perhaps even contributing to planets where life might arise. In this way, neutron star mergers connect the deaths of ancient stars to the formation of new worlds, closing a cosmic cycle that spans billions of years. The zombie stars don't just persist as remnants. They actively participate in chemical enrichment, contributing heavy elements that no other process can produce in significant quantities. Zombie stars exist in a state between activity and inertness. They're no longer burning nuclear fuel like active stars, yet they're not completely passive. They emit radiation, they interact with their environments, they provide laboratories for studying physics at extremes. They represent a particular phase in the universe's evolution, a phase that will dominate the far future when star formation has ceased and stellar remnants outnumber active stars. The regularity of pulsars, the violent outbursts of magnetars, the periodic eruptions of accreting white dwarfs, all of these phenomena arise from objects that have officially died by the standard of stellar evolution. Their continued activity demonstrates that death for a star is not cessation, but transformation. The energy sources change from fusion to rotation, from chemical potential to gravitational accretion, but the objects remain dynamic, observable, studyable. Each zombie star carries within it the history of the star that formed it. The composition of a white dwarf reflects what elements its progenitor star produced through fusion. The rapid rotation of a pulsar preserves the angular momentum of the collapsing stellar core. The magnetic fields of magnetars amplify and preserve the fields that existed in their progenitor stars. These remnants are not just ends, but also records, preserving information about stellar processes in forms that can persist far longer than the stars themselves. Understanding zombie stars requires drawing on nearly every aspect of astrophysics. Their formation involves stellar evolution and supernova physics. Their structure requires nuclear physics and general relativity. Their interactions with companions involve binary dynamics and mass transfer. Their observational properties span the electromagnetic spectrum from radio waves to gamma rays, requiring coordination between different types of telescopes and observing techniques. They're integrators of physical knowledge, objects where multiple fields of study converge. The discoveries continue. Each improvement in detector sensitivity, whether for electromagnetic radiation or gravitational waves, reveals new examples or new properties of zombie stars. The population of known millisecond pulsars grows as surveys become more sensitive. Magnetars are identified in other galaxies, revealing that their formation is a universal process. White dwarf merger progenitors are discovered through precise measurements of stellar motions and brightnesses. The field remains active, with new observations regularly refining or challenging theoretical models. For those who study them, zombie stars offer rewards beyond scientific knowledge. They provide perspective on time, scale, and transformation. They demonstrate that endings can be beginnings, that systems can persist and remain active through mechanisms different from their origins. They show that the universe is more creative and diverse than any single model might suggest, constantly producing phenomena that challenge understanding and require new explanations. As you rest, perhaps these thoughts provide a particular kind of comfort. The universe contains objects that endure beyond their expected lifetimes, that transform rather than simply ending, that find new sources of energy and new ways to interact with their surroundings. Stars die, but they don't disappear. They become something else, something that persists for timescales that make their original lives seem brief. In this persistence, there's a lesson about continuity and change, about how endings are also transformations. The zombie stars continue their existence, spinning in space, cooling gradually, occasionally revealing themselves through bursts of radiation. They're monuments to the stars they once were and harbingers of the universe's ultimate state. They're objects of scientific study and sources of philosophical reflection. They're reminders that death is not absence, but transformation, not ending, but transition into a different kind of existence. Thank you for listening to this exploration of zombie stars. If you found this journey through stellar remnants and extreme physics relaxing or interesting, consider liking this video and subscribing to Nebula Nights for more astronomical content delivered in this calm, detailed style. The universe is vast and filled with wonders, and there's always more to explore together. Until next time, rest well, and when you look up at the night sky, remember that scattered among the points of light are objects that refuse to fade quietly, that persist and remain active through means different from normal stars, that demonstrate the universe's capacity for transformation and endurance.